Hey everyone, so today we are going to finish off chapter 6 looking at non-metal oxides and metal oxides in water. So what happens when you have different types of oxide compounds, so compounds with oxygen in it, and then they're in water obviously. Okay, so first of all, when we say metal oxides, you have to remember that metallic oxides are basically ionic compounds, right? So you have a metal with a non-metal, just so happens to be that the non-metal is oxygen, right? So for example, uh, lithium oxide, let's see, right? So this is an ionic compound. This is also considered to be a metal oxide. A non-metal oxide is where you have essentially anything that has oxygen with a non-metal element. So for example, sulfur dioxide. Okay, so let's take a look at what happens when we have the different substances reacting with water. Okay, so a basic anhydride. So metal oxides, okay, especially those with a metal from group 1 or group 2, so the alkaline metal and the alkaline earth metal family, except beryllium, will react with water to produce a basic solution. So essentially what ends up happening is when that compound dissociates in water, so here's an example of dissociation again, right? So it's basically where you have the ionic compound that is dissolving, forming the ions. What really happens is that the oxygen, so the sodium is a spectator, right? So the sodium is not doing anything with water, does not hydrolyze, but the oxygen ion will hydrolyze with water. So what ends up happening is the oxygen takes on, it almost behaves like a base, right? So water behaves like an acid and donates a proton. And then the result of that is actually hydroxide. So the oxygen becomes OH and the water also becomes OH, right? So the net, the overall reaction, if you consider what's happening here, when you have sodium oxide dissolving in water, you essentially make sodium ions, which we don't really consider, but we're making hydroxide. So obviously this is what is creating a basic solution, right? So the term that we can use, so anhydride is a very generic term that means not in water. So when we put it in water, right, we have the hydrolysis occurring. So a basic anhydride would be like a solid compound that is not yet added to water that will create a basic solution when it is added to water. So these oxides are referred to as basic anhydride. All right, so let's talk about some exceptions to this rule. So amphoteric metal oxides and high oxidation numbers. So when we talk about metal oxides with high oxidation numbers, some of them are included in group 2. So actually, beryllium is one of these exceptions to the rule, which is why over here it was mentioned, right? Except beryllium, right? So beryllium does something different. Okay, we're going to look at this. So elements that have high oxidation numbers, which you don't fully understand yet, that's actually in chapter 7. Think of right now, just to simplify things, think of oxidation number as charge. So for example, aluminum has a charge of +3 when it's an ion. So that would be considered to be something that has a high oxidation number. Usually anything +3 and up. So we know from doing our weak acid equilibriums that +3 and up elements or cations will generally make acidic compounds, right? They behave like weak acids. So this is no different here. So when you have a metal oxide, they can behave as either acidic oxides or basic oxides. And that's because what's happening is, just for example, aluminum oxide. The aluminum ion behaves like an acid, and the oxygen ion will behave like a base. Like both of them are hydrolyzing again, right? So this is very similar to when you have other ionic compounds where you have both ions that are hydrolyzing It's just in here, it's a specific case that we're discussing because they're oxygen ions. Okay, they kind of have their own little section in our book here, right? But very, very similar. You have two hydrolysis reactions. So, yes, of course. So if we look at all of these, so all of these have high charges. So beryllium is the only one that does not. It's in group 2. But chromium, +3, right? Aluminum, we already discussed, is +3. Gallium, in this case, this is gallium 3. This is tin 4 and lead 4. So anything +3 and up. With the exception of beryllium, it's the only one that's +2 that undergoes this. Right. So here is an example where we have manganese oxide, and actually this manganese is a charge of +7, which is one of the rare ones. We don't usually see that too much. But the +7, when it reacts, it's definitely behaving like an acid. And same thing, chromium 3. Chromium 3, this is behaving like an acid. So technically you have the oxygen that is also hydrolyzing. Okay, but if, for the most part, your acidic oxide is going to become it's going to become acidic more so than basic. But technically, both processes are happening. Okay, now I'm not going to go into detail about assigning oxidation numbers. I don't think it's necessary for what you need it for in this chapter. If you find it's necessary when you're doing the review questions, just don't worry about it for now. I don't believe that they ask you for assigning numbers. It's more about recognizing the charges at this point. Okay, we will spend like the whole first part of chapter 7 is like identifying oxidation numbers, so don't worry about that. Okay, so let's look at acidic anhydride. So remember, this is going to be basically a compound that is not in water yet, that when it is in water will create an acidic solution. So non-metal oxides will react with water to produce an acid. Okay, so this is an important point here as well. In general, as the elements become less metallic, their oxides that react with water produce a more acidic solution. And you literally look at where that element is located on the periodic table. So as you go to the right in a period on the periodic table, your elements become less metallic and more non-metallic, right? The further to the right we go, the less and less metallic the properties are for that element, okay? In addition, so that's going across a period, going from the bottom to the top up, so going in this manner, right? You have more metallic at the bottom, right? They behave more like a metal, and more non-metallic towards the top. Okay, bottom and top up. Okay, so let's take a look at this image here. So here we have SO3, which is a non-metal with oxygen, and this is going to create an acid. Okay, they don't always create a strong acid, but when it hydrolyzes, it will produce some form of acid. Okay, so let's take a look at these here. So we have two different reactions that we're going to then complete. So you have to recognize this is a metal with oxygen. So we know that this is going to create a hydroxide, right? So potassium oxide and water will create potassium hydroxide. Okay, you don't have to write this out as the net ionic equation. We should, though, balance. I believe that is already balanced. We have 2 oxygen, 2K, and 1, 2H. Yep, so that's good. Okay, for B, we have a metal again. So metal with oxygen, so it's magnesium. So it's not beryllium, which means it's not an exception. So this is going to create magnesium hydroxide. And you would do crisscross rule as normal. And then I think this guy's already balanced. Yes. Okay. This is a really good question, number 2. So it says, which of the following third period oxides? So all of these elements are located in period 3, and they're going to react with water. Arrange these oxides in order from least acidic to most acidic. Okay, so remember this goes back to this point here. The less metallic their oxide, the more acidic the solution is. So really, this should be the most metallic. This should be the most non-metallic, right? So the further to the right that we go, you should have a higher acidity. So here, the least, of course, is going to be aluminum. So all of these are non-metals. Oh, this is a metalloid. So non-metal, non-metal, metalloid. Well, you know what I mean by that. Non-metal. And then, of course, aluminum is a metal. So off the bat, we know that aluminum oxide here is going to be the have the least acidity, right? Actually, it's going to make well, it's actually still going to be an acid because it has the aluminum +3, but it's just not as acidic as the others for the rankings, right? Next, you're going to have your metalloid. All of the other ones are non-metals, right? So this is going to be silicone dioxide. Okay, then for the 3 non-metals, you're going to rank them based on their placement on the periodic table. So remember, as we go to the right, it becomes less metallic. So we're going to have the phosphorus, then the sulfur, and then the chlorine, right? Chlorine is a halogen. So of the ones listed here, it is going to be the most non-metallic. This is the furthest to the right. Okay, so B says 2 of the above oxides react with water to produce strong acids. Write the balanced equations for those reactions below. So the ones that are going to be the strong acids, this should make sense to you, are the ones that have the most non-metallic properties. So if it's creating a strong acid, you basically have to look at your list of strong acids, the ones that we know are strong, and then think about what these would make. So obviously, SO3 is going to react with water to produce the only strong acid that has sulfur in it, which is sulfuric acid, right? And then our chlorine oxygen molecule is going to react. So this looks very similar already to a polyatomic ion. I mean, it's not exact, but this is not going to make hydrochloric acid. Hopefully you recognize. It's going to make something that has oxygen in it, right? So this is going to make perchloric acid, so HClO4. And of course, we should be balancing these and being, actually the first one's already balanced, but this guy here, I think we need a, 2. So that's 8, 2 chlorine, 2 hydrogen. There you go. Okay. Number 3, so it says in general, so we're just going to fill in the blank with either the word ionic or molecular. Of course, you know that molecular is where you have only nonmetals. Ionic, you have a metal, nonmetal. So we have, in general, ionic oxides react with water to produce ionic bases, right? In general, molecular oxides that react with water, acids are molecular. Right? There's no metals in an acid structure. Okay, so we will continue with part 2. So there's not much more to go here, actually. I wish I could just kind of squeeze it into this one section, but there is quite a long block that discusses acid rain in your book. I do expect you to read through that theory, and we're going to go through the practice problems in the next section.